Okay, let's use a triple integral to find the volume of the given solid. We're going to do part B. The solid surrounded by the cylinder x squared plus y squared equals 4, and the planes y plus z equals 5 and z equals 1. And in this particular problem, I think I can get away without graphing the full 3D picture. Let me show you what I mean. I'm going to start by graphing this plane and this plane in just the YZ plane, which means this plane will degenerate to be a line, y plus z equals 5 in the YZ plane. So the intercepts would be 5 on both axes. And you could represent then that line like so. And then, of course, if you wanted to draw the full 3D picture, you could run this generating line parallel with the x-axis, and then the plane would appear to be leaning against the plane y plus z equals 5 would appear to be leaning against the coordinate plane given by the x and the z axes. But I don't think I need to draw that. I'm also going to draw z equals 1 in just the YZ plane. There you go. That's z equals 1 in just the YZ plane. And of course, this line is y plus z equals 5 in just the YZ plane. And then also there's the cylinder. Everything takes place within the confines of the cylinder. But in the xy plane, this cylinder, x squared plus y squared equals 4, is just a circle of radius 2. So I think I'm just going to draw, at least for now, I'm just going to draw the circle of radius 2 in the xy plane. And so I'll do that in green here. Okay. So this line is actually above that circle. Okay. So what's what here? Well, I think I can use this line y plus z equals 5 as my roof and z equals 1 as my floor. What do I mean by that? Well, remember when we set up the integral, it's a triple integral we're going to use to find volume. So the integrand is 1. We're going to go with the usual differential order, dz, dy, dx. So the roof and the floor give the limits of integration on the inner integral. And because we're integrating with respect to z first, they should be height values. Z in terms of functions of x and y possibly, or maybe a constant. And then I can see from my picture, as long as I stay within the confines of the circle here, or the cylinder in space, the floor would be given by any point along z equals 1, or in the plane z equals 1 if you were looking in space. And the ceiling or roof would be given by any point on the line y plus z equals 5, or in space on the plane y plus z equals 5. And so the bottom of this line, this vertical line segment, gives me my lower inner limit of integration, and the top of it gives me my upper. So the lower limit of integration on the inner integral is just 1. The upper, I need to solve this for z. Get it in terms of y in this case. In other cases, it could be in terms of both x or y, or just x. So my roof or ceiling is just 5 minus y. Okay, so inner upper limit of integration, 5 minus y. Now, if I project the solid region that I would get by intersecting the full cylinder with these two planes, if I project that region down onto the xy plane, then it has to lie inside this circle given by the cylinder in the xy plane. Which means all I really need to draw then is the region of integration that I'm integrating over with respect to x and y. And that's just going to be a circle of radius 2. Well, technically it's a disk, I guess. Radius 2. So I can use this disk to help me set up my limits of integration on my outer two integrals. Now, for now, since we haven't, at this point in section 5.6, or 15.6 rather, we haven't talked about cylindrical coordinates, I'll just say my region R then is the disk x squared plus y squared is less than or equal to 4. That's what describes this disk. And then I'll actually switch to polar at some point during the evaluation of this integral. Okay, so let's evaluate the integral. All right, here we go. Let's evaluate the inner integral first. And of course, we integrate 1 with respect to z. We just get z. And everything else comes along for the ride. I could just make it r down here and not worry about writing the disk all the time. If you can do that if you want, no problem. And then you get z when you integrate with respect to z, when you integrate 1 with respect to z. But then you're evaluating from 1 to 5 minus y. And you still have dy dx on the end for now. Okay, so what does that become? That becomes, if you plug in the upper limit of integration, you get 5 minus y. You plug in the lower, you get minus 1. So that's 4 minus y when you combine them. dy dx. Now, you'd be crazy to integrate in rectangular coordinates here over a disk, over this disk here. So let's set it up as a polar integral. And we know if we draw on a spoke here, you could think of it as a representative sector, that r is going to range from 0 to 2. And if you think angularly, theta is going to run from 0 all the way around to 2 pi. So when we set this up, we get 4 minus y becomes 4 minus r sine theta, because y is r sine theta in polar coordinates. The area element dy dx, or dA, becomes, remember, an extra factor of r and then dr d theta. And then as we just said, r runs from, if you look at the picture, 0 to 2, 0 to 2 all the way out. And so that means the inner limits become 0 and 2. And then theta runs all the way around, so 0 to 2 pi. So we evaluate that integral, and we're done. Okay, so there's no way to separate this, so let's just distribute the r. Get 4r minus r squared sine theta in parentheses, and then dr d theta. And then just integrate with respect to r. So the outer integral symbol stays where it's at. We get 4r squared over 2, or just 2r squared for the first term, minus, let's say, 1/3 r cubed sine theta. And that's going to be evaluated from 0 to 2, right? Okay. So if we do that, if we plug in 2, I guess we get 8 for this first term, and then minus 8/3 sine theta for the second term if we plug in the upper limit. If we plug in 0, everything's just going to zero out, isn't it? So we're left with the integral from 0 to 2 pi of 8 minus 8/3 sine theta, d theta. So we're integrating with respect to theta. So if we do that, we'll get 8 theta. The integral of sine theta is negative cosine, but we already have a minus, so it'll make it plus 8/3 cosine theta. And we evaluate that from 0 to 2 pi. And if we plug in 2 pi, we get, what do we get? We get 16 pi for this first guy, plus, okay, just cosine of 2 pi is 1, so just plus 8/3. And then if we plug in 0, 8 times 0 is 0. Cosine 0 is 1, so we just get plus 8/3 again. And the 8/3 are they're going to knock each other out, aren't they? So we're just going to be left with 16 pi.